So this is Lab 10, the buffer lab. We have a choice of how we do it. Even on campus, sometimes I choose to do this as a dry lab. These are fairly complex systems with a lot of different, we've talked before about the issues about sometimes things act to completion and are stoichiometric ratios, and sometimes it's an equilibrium and we need to use equilibrium calculations. And understanding all of the different acid and conjugate base species and what they do can be pretty complex. So rather than actually doing any wet chemistry, we're just going to walk through some of the steps of what we could do, and we're not going to get into actually making these buffers, nor are we going to add things to the buffers. So in this lab, I am going to use carbonic acid as the weak acid and sodium carbonate as the conjugate base. I'm going to use a 0.4 molar solution of carbonic acid and a 0.5 molar solution of sodium carbonate. I'm going to aim for a target pH of 5.80. Now this is not the weak acid conjugate base system you're going to use. And of course there's a little bit of an issue with it in the sense that this technically is a diprotic acid, but we're just going to consider it as if it's a monoprotic acid and only talk about the first deprotonation. You're going to use formic acid and sodium formate, which has a different Ka value than carbonic acid. And each of you is going to be assigned a different molarity. Each lab group is going to have a different stock concentration of formic acid and sodium formate and a different target pH, which will change your calculations. Okay, so the first question is asking, what do you expect in general for carbonic acid solutions? Do I expect them to be acidic, basic, or neutral solutions? And it's hinting justify with a dissociation equation. So when I'm I have no idea what this is asking, let me just say, what does carbonic acid do? Well, if I put it in water, it creates protons. That's what acids do. They donate or produce protons. Of course, the proton in water is going to be in the hydronium ion form, so I'm going to have H3O plus, and my hydrogen carbonate ion is my conjugate base. This is what's left over after I pull off one proton off of the carbonic acid. Well, the fact that it makes hydronium ion and the pH in the acidity is controlled by how much hydronium ion I have. If I have an excess of hydronium ion, it's going to be acidic. If I flip the question and say, well, what about the sodium hydrogen carbonate solution? Is it going to be acidic, basic, or neutral? Again, let's consider, what does the hydrogen carbonate ion do, the conjugate base of carbonic acid? When I put it in water, it's considered a base because it's going to produce hydroxide ion and it's going to regenerate carbonic acid. So this is sort of the flip version, only I have water involved as well. Again, the fact that it makes hydroxide ion and pH and acidity and basicity is controlled by whether I have an excess of hydronium or an excess of hydroxide ion suggests it's going to be basic. But what happens if I mix them together? So if I take a solution that's got roughly equal concentrations of carbonic acid and sodium hydrogen carbonate, what do I expect about that? It says justify your answer with a less than 10-word explanation and a mathematical equation. Okay, the fact that it says mathematical is suggesting I kind of got to get into the nitty-gritty for this. I know what they each do independently, and I know that this is a system in equilibrium, so my carbonic acid is a reactant in this reaction, and the hydrogen carbonate ion is the product, and this is in, and I also know something else. I know the Ka value of it. And I also know that the Ka expression in this case is the hydronium ion times the hydrogen carbonate ion divided by the carbonic acid concentration. But if I have roughly equal concentration, what I'm really saying is that the hydronium ion concentration is equal to the Ka. And I know that things are acidic if the hydronium ion concentration is greater than 10 to the negative 7, and basic if it's less than, and neutral if it's equal to. So and I know that the Ka here is 4.4 times 10 to the negative 7. So it is greater than 1 times 10 to the negative 7. Not by a lot, it's still in the 10 to the negative 7 range, but it's 4 times greater. So this would be acidic. I also could have approached it from a different mathematical equation. I could have considered the Henderson-Hasselbalch equation. Essentially, this is if I take this and write the log-based version of it and do some rearranging. And here I'm making the assumption the difference with the Henderson-Hasselbalch that makes it only sometimes appropriate to use is that we're saying that the equilibrium concentration of the conjugate base is close enough to the initial concentration to say, go ahead and just use the initial concentrations. So this is only true for weak acids, and it's only true if these are in reasonably comparable proportions, so I think at most a 10-to-1 ratio difference. So in this case, I'm really kind of saying the same thing. If the conjugate base and the acid concentrations are the same, they cancel out. Of course, the value of 3/3 or 27/27 or whatever it is has a mathematical value of 1, and I have to be careful. Taking the log of 1 is 0. So this is really the pH is equal to the pKa. So I can just find out what the pKa is by taking the negative log of my Ka, and it turns out to be, I think it's 6.36. I didn't write it down, but it's less than 7. And I can also tell that, remember, from here, I'm looking here, it's going to be the negative of the exponent, but because of the 4.4, it'll be a little bit less than 7. So either way, I come up with the fact that in this case, buffer solution, because it's a mixture of a weak acid with its conjugate base, is going to be acidic. Now, that answer is going to change depending on which specific weak acid conjugate base system you use and what its Ka value is. If you had a Ka value, if it was a very, very weak acid, and the Ka value was like 10 to the negative 8 or 10 to the negative 9, then it turns out it would be basic. All right, now we want to get into the nitty-gritty and actually compute the pH of the carbonic acid solution. Again, in question number 1, we revealed that we're expecting it to be acidic, but now we're going to actually get into the math of it. We're also reminding you that if you use the 5% approximation, you need to make sure and check whether that's a valid approximation to make. So again, our starting reaction is carbonic acid dissociates and forms hydronium ion and hydrogen carbonate ion. And in my case, I'm starting with a starting molarity of 0.40 and nothing because I'm just have carbonic acid. So this is some of it's going to dissociate, whatever the equilibrium determines, and I'm going to just say X is going to dissociate, and that means I'm going to increase by X over here. I'm going to write out my expression based on the reaction with my concentration of my products divided by the concentrations of the reactant. Since this is water, it doesn't get included, it's a liquid. And I get X squared over 0.4 minus X. So here is where I'm going to make the 5% approximation, or the weak acid approximation. We're saying that this is a weak acid. It only slightly dissociates. That means X is small. And if X is much smaller than 0.40, then essentially the value of this is going to be 0.40. So I can make that assumption, try it out, and then when I'm done, I'm going to actually see is X actually less than 5% of 0.40. All right, so notice that in this case I'm solving for X, and X is equal to hydronium ion concentration. It's going to be the Ka, and multiply both sides by 0.40 to isolate X squared, and then I take the square root of it. And I end up with a value of 4.195 times 10 to the negative 4. But I want the pH, and this is the hydronium ion concentration. So I'm going to take the negative log of it, and I get a value of 3.38, which is less than 7. So this is, in fact, an acidic solution, as we expected. Now I want to go back and check, did I make a good approximation? So I'm going to calculate the percent ionization, which is how much is X compared to the starting initial concentration of my reactant, in this case, the carbonic acid. And it turns out, if I multiply it out, it's 0.1%, which is well below the 5% limit. Now, if I had gotten 5 or 6 or 8%, that would suggest that this is no longer something I can ignore, the fact that I subtracted off X, and I'd actually have to use I'd have to leave it as, solve it with the X included, and I would need to do a quadratic equation to actually calculate the true value. We're going to do the same thing for the sodium hydrogen carbonate. Now this is a conjugate base. We decided we're expecting it to be basic, but let's see. Now with conjugate bases, everything gets a little bit trickier. First of all, my starting reaction is producing hydroxide ion, not hydronium ion. And I'm also happen to be starting with 0.5. Oops, here's a typo. This should be 0.5 minus X, not 0.4 minus X. I copied and pasted. So when I write the expression, I'm now looking at the K for this expression. Since this is a base, we call it KB rather than KA. And I don't have that value. I was given the KA of this, which is really talking about mostly the reverse reaction. Now, it's not only reverse, but I also have some water splitting going on there. So I can calculate KB as KW divided by KA, but I'm going to actually need to calculate the KB and use that number. I do the same weak base approximation and say that X is much smaller than 0.5, so I'll just call this 0.5. Notice now I'm solving for X, but X is no longer hydronium ion concentration, it's hydroxide ion concentration. I get a value of 1.07 times 10 to the negative 4. Notice here I calculated KB as 1 times 10 to the negative 14th divided by my Ka. But now I'm going to take the log of it, and I'm not going to get the pH. I'm going to get the pOH, which is 3.97. It didn't ask me for the pOH, it asked me for the pH, but I know that the pH and the pOH always add to 14, so I can subtract the pOH from 14, and the pH is 10.03. And it is basic, that's what we were expecting. Okay, now let's check, did we do a fair approximation? So if I solve for X, which is 1.07 times 10 to the negative 4, that's the amount dissociated, over the original concentration of the base, it turns out to be 0.02%. Again, well below the 5% rule, so this was a fair assumption to make. Now we're going to actually start talking about making the buffer. I want to make a buffer with a target pH, in my case, of 5.80. And so this is referring to, when we say the ratio, we mean the ratio of the conjugate base over the conjugate, the ratio of the conjugate base concentration to the weak acid concentration. And this, of course, when I mix them, I'm going to have some dilution from mixing the two, so I have to take that into account for these. And note that if I call this the ratio and do some rearranging, I get a formula that says the ratio is equal to 10 to the pH minus the pKa. The pH is my target pH that I want my buffer to be, and the pKa is the pKa of whatever system I'm using. So in my case, if I take the negative log of 4.4 times 10 to the negative 7, it's 6.36. 5.8 is my target pH. That turns out to be a negative 0.56 difference, or a ratio of 0.2754. So in other words, this ratio means that if the ratio is 1, I would be having equal concentrations. This is now, the base is 27% of what the acid concentration is. So I'll use that ratio now to figure out, well, how much volume do I need? And I have to build in the fact that it's not just mixing. I can't just take 27.5 milliliters of the conjugate base with 100 milliliters of the acid. I actually have to build in the fact that I need 100 milliliters and the fact that it's going to dilute when I mix them. Now I'm going to do this calculation assuming I want to make 100 milliliters of a buffer, but yours I think is using 200 milliliters, but the method will be the same. So the formula, with a lot of rearranging, and I highly encourage you to just know this version of the formula rather than trying to do the math on your own. I need the volume of the buffer. In my case it's 100. The molarity of the base, in this case the conjugate base is my hydrogen carbonate, 0.5. The molarity of the acid, that's 0.4. My ratio that I just calculated on the last problem, plus 0.5, the molarity of the base. And I get a value of 81.94 milliliters for the acid, for my carbonic acid. I can get the, that should be VB. Sorry, that should be VB. The volume of the base is, I know I want 100 milliliters. Well, if 81.94 milliliters is the acid, the base is what's left over, which is 18.06 milliliters. And so I just kind of, in this case, my acid is carbonic acid and my base is sodium hydrogen carbonate. Okay, so now we assume that we've actually prepared the buffer according to our specifications. We've taken our 81 milliliters of the carbonic acid and the 18 milliliters of the conjugate base, and we're going to add some water to it. So the question is, if distilled water is added to your buffer, what's going to happen to the pH? And it says, justify the answer with a less than 15-word explanation and a mathematical equation. So it's suggesting the math is really going to basically tell me the answer. So what equation would be the right equation? Well, let's use the Henderson-Hasselbalch equation. And let's think about what's going to happen. So my conjugate base, I started with 0.5 molar, but then when I mixed it in ratio of 18 to 100, I diluted it. Same thing with my acid, I started with 0.4 molar. So this is referring to the concentrations after I diluted it by mixing. So I want to see what's going to happen to that if I add some water. Well, water is just going to dilute it, right? So I can get some math in here and take V1 milliliters of buffer and X milliliters of water to show you what's going to happen. But it's going to dilute the conjugate base and acid equally. So if I actually were to calculate it out, notice I have this factor on the top and on the bottom, and they cancel out. So I end up with the exact same, exact same ratio that I had before. So this will be the same, whatever the pH was before the water, it's going to be the same. It's not going to change the pH. Okay, what if instead of water, I took some of my buffer and I added some strong acid? Is the pH going to increase, decrease, or stay the same? Again, I now need to think, how are my concentration, my conjugate base concentrations and my weak acid concentrations going to change? In this case, the strong acid is going to react with some of the components. So first of all, I put some strong acid in there. I'm using HCl, but it doesn't particularly matter. It's going to dissociate 100%, and all of it's going to be converted into hydronium ion concentration. But we know that the hydronium ion can react with the hydrogen carbonate ion with the conjugate base to form water and the carbonic acid. So my conjugate base concentration is going to go down a little bit because I reacted some of it away. And the carbonic acid concentration is going to go up a little bit because I produced some of it. So this top number is going to go decrease, and the bottom number is going to increase. Overall, that ratio is going to decrease. When I take the log of a smaller number, I'll get a smaller log value. So overall, it's going to decrease. So my pH is going to decrease somewhat. It's not going to decrease very much because this is a ratio of the change, and then I take the log of the ratio of the change. So it's not going to have a huge effect, but it is going to change. What if instead of strong acid I add strong base? Again, what's going to happen? Well, it's the same idea, except that now I have to consider what happens to strong bases and what will they react with. Again, I'm going to use NaOH as an example of a strong base. It could be another one though. But I do know that strong bases produce hydroxide ion, and all of it will dissociate into hydroxide ion. And then that hydroxide ion can react with the carbonic acid, producing more of the hydrogen carbonate ion. So my carbonic acid concentration is going to decrease a little bit because I'm reacting it away, and my hydrogen carbonate ion, my conjugate base concentration, is going to increase a little bit because it was produced in the reaction with the hydroxide ion. So the top value is going to go up, the bottom value is going to go down. Overall, the ratio is going to go up a bit, and when I take the log, that's going to go up a bit. So my pH is going to increase a little bit. Therefore, I expect that the pH will increase slightly. Okay, so that's kind of talking about it generically and conceptually, but can I actually mathematically do this? So I'm going to calculate this in the same way that we did. So I'm going to use this example. I'm going to figure out what is X from my NaOH. I'll figure out what is X. Remember, there's another dilution. And then I'm going to figure out what is the resulting concentration after I subtract off this X that reacted away, and I add some of this X. So I'm going to calculate these and come up with it. But I now need to actually remember that I diluted it a couple of times. So the first time I diluted it is when I mixed my stock concentrations together to make the buffer. And so that changed, there was a dilution of mixing. And then when I add in the strong base, I essentially diluted it again because I added in a little bit more volume of the base. So I'm going to have to do these calculations. And they're simple dilution M1V1 over V2 calculations. So here I started with my stock concentration. I had 18.02 milliliters for a total of 100 milliliters of the buffer. I diluted again I took 21.6 milliliters of my buffer, and it was already at this concentration. When I add in the 0.65 milliliters to the 21.6, I get 22.25. Again, we're assuming volumes are additive, even though they're technically not quite, but they'll be pretty darn close. So this is my adjusted diluted concentration. Now, this isn't even taking account that it's going to react with the, it's going to be produced in that when it reacts with the hydroxide ion. This is just what is it in the solution before I add, well, after I add the base, but before the base reacts with anything. Doing the same thing with the acid. Again, first we had our stock 0.4 molar, 81.94 milliliters, total mixing volume of 100, and then I add in, take 21.6 of that, and I add in the 0.65 milliliters of the base, and I get 0.3182 molar. Now I need to consider, but what about that reaction? Remember, all of the NaOH reacts with a weak acid to form conjugate base. Let's figure out how much NaOH we actually added. So again, I'm going to consider the diluted volume, 0.24 times 0.65 milliliters, divided by 22.25 milliliters. So effectively, my concentration of NaOH added after mixing was 0.007 molar. So for the base, remember, the sodium hydroxide reacts with the weak acid and makes base. So I'm going to add 0.00701. It reacts with the acid, so I'm going to subtract 0.00701. So now these are the concentrations that I can plug into the Henderson-Hasselbalch equation and get a value of 5.84. Okay, refresh. Remember, what was it before I added? My target pH was 5.80, so that was the buffer pH before I added the base. After adding the base, it was 5.84. So the change in pH, I'm going to take the final minus the initial, and it went, so it's 0.04, so that means the pH went up slightly. Well, that was what we predicted would happen. Just as a comparison, let's see what would happen if we had done the same thing, but instead of using a buffer, we used distilled water. So we're going to replace the buffer by an equal volume of distilled water, but the same basic things. Well, here, the NaOH doesn't have any species to react with. It's in water. There isn't anything for it to react with. So this is just what is the pH of the diluted solution. Again, I had to calculate the dilution factor. So my diluted concentration of NaOH is 0.00701. And I know that for every NaOH, I produce a hydroxide ion. So the concentration of hydroxide ion is 0.00701. If I take the negative log of that, that'll get me the POH. Remember, because this produces OH, I'm solving for the POH. Again, to get the pH, I subtract that from 14, and I get 11.85. Just to recall again, I really can't compare the pHs. I have to think about comparing the change in pH. So water would have started with a pH of 7 because it's neutral. After adding the NaOH, the pH went up to 11.85. If I subtract final minus initial, I get 4.85. So the pH changed by 4.85 pH units. That's going up a lot. Remember, each unit of pH is a factor of 10. So that's a factor of 10 to the fourth in increase. That's a substantial change. Okay, so that's the numeric version. Now, the last part to wrap this up is to simply say, okay, explain 11 and 12 in terms of the definition of a buffer. I will give you two definitions of a buffer. These are two ways we typically define it. One is by what a buffer does. The purpose of a buffer is it's a solution that resists change in pH when the acid or base is added to it. Well, we saw that. It resisted pH, so I had only a 0.04 compared to a 4.85, you know, a substantially smaller pH change. The why is because it has species in there that it can interact with. If I add strong acid, it can react with the conjugate base to neutralize some of that strong acid. If I add strong base, it can react with the weak acid to neutralize the strong base. And so the components of the buffer are interacting with the added acid or base to make sure that the pH doesn't change by very much. Because I have a system in equilibrium, those weak acid and conjugate base concentrations can adjust and maintain equilibrium up to a point. Another definition of a buffer is it's an aqueous solution consisting of a mixture of a weak acid and its conjugate base, or vice versa, a weak base with its conjugate acid. Using this one, we saw that the reason why I need a weak acid and its conjugate base is that I have to be dealing with a system that's in equilibrium to be able to use that Henderson-Hasselbalch equation and to be able to use the fact that the Ka is going to interact with it. My two components now can interact with, the weak acid can interact with any strong base that's added, and the conjugate base can interact with any strong acid that's added. So I need both components that can kind of regenerate each other through that reaction in equilibrium in order to stabilize the pH. So this is two ways of looking at it. This is sort of the effect that we get, and this is the how do I make a buffer type of definition. And we see that buffers kind of have a very interesting, unique chemistry that's very powerful. It's extremely powerful in the human body, and I hope that you've gotten a sense of what buffers are, what do they do, and how to handle some of these calculations with them.